Hello everyone and welcome to the webinars hosted by EDB. My name is Monica and I am part of the marketing team here at Enterprise DB. I will be your host for today's webinar, Beginner's Guide to High Availability for Postgres. I am joined by Gabby Childers today, Senior Sales Engineer here at EDB. Before we get started, I just want to go through a few housekeeping items. This presentation is being recorded. We will be sharing the recording along with the slides after the broadcast. The lines are currently muted. If you have any questions, please feel free to submit it in the questions panel. Today's session is scheduled for 1 hour. We expect the presentation to last most of our time today, and we will allot any extra time for Q&A. If we do not have time to address all questions, we will follow up afterwards with any attendee whose question was not answered. And now, without any further ado, Gabby, over to you.
Thank you for the introduction and welcome everyone. As Monica stated, this is a session that we do in our regular series of webinars, and we will be having new webinars on different topics in the coming weeks, and we'll tell you more about them later. First of all, a bit of background. As stated, the housekeeping items are on your screen right now. But I also want to add that due to this rather strange time, I'm doing this webinar from my home. So if at any time you hear strange background noises, that unfortunately is unavoidable. It's a consequence of not being in an office. I hope that doesn't disturb the following through, and apologies also for the slight strange view of my background because there is sunlight streaming into this room that I can't block. So, on the topic of today, what we're going to discuss today is the topic of HA, high availability. And what we're going to talk about is what it really means to be highly available, what the measurement criteria are for high availability, how it works, at least for databases, how you can achieve high availability with Postgres and our EDB tools. I'm going to talk a bit more about the technical details of that and how to keep an eye on high availability using our tools. And I'm going to show you some scenarios for things like upgrading where you are expected to have some interruption of service and how you can mitigate that. So talking about high availability, what is interesting is that although it's formally a well-defined concept, as you can find through research, people do have some different outlooks on what high availability means in practicality. But let's look at the formal definition first. So high availability is defined as a characteristic of a system which aims to ensure an agreed level of operational performance, and that's usually uptime, for a higher than normal period. And this is already contentious because what is normal? And for which parts of your business which levels of HA are required, for instance. So we're going to get into that, and what we're going to talk about is what are the key principles to achieve high availability, and what are the risks and issues that you might come across when you look into achieving high availability. More practically speaking, in computing, the term availability is used to describe a service normally, and it's described as a continuous and consistently correct functioning of a system or service as provided to its users. However, you can measure high availability as a value, but what are you measuring on? And that again is one of those contentious questions, because are you just looking at the hardware, the underlying hardware, and how available it is? Or are you more interested in the IT infrastructure, for instance, things like networking? Or are you in the end just interested in how available the business application is? So the end-to-end availability of an application. All of these have their own way of looking at what is important. And we'll get back to those measurement criteria later on in the slides and the discussion afterwards. But first, I want to take you through some of the things that influence high availability, independent of what the item is that you're measuring on. And what we're looking at here is a split into two categories of interruption of service. One is a scheduled or planned downtime, which results, for instance, from maintenance or other operations that cannot be done while the system is running, is active, right? And when it gets to the hardware or the infrastructure, those include things like rebooting or reconfiguring a network or other changes in the environment that you must make. Whereas from the business side, business application side, it's, for instance, a case where the application isn't needed at certain points in time because in a weekend there is no business. So in that case, if the application is unavailable, that is not an issue to the business. The other side of that coin is unscheduled and unplanned downtime. And these are the results of things going wrong. Whereas with scheduled and planned downtime, you had an idea about how to get from operational to non-operational to operational again. In unscheduled downtime, what happens is that a part of your infrastructure is misbehaving, and as a result, the service is interrupted. If you really want to make a good calculation of where you want to be with your availability, you must first make a very good overview of all the aspects of your operation that can influence downtime. And why do I say this? Because if you look at just one of these aspects of your availability, you may be surprised when something goes wrong that was outside of your view and where you then run into an issue that you didn't expect and where you get downtime from, even though you thought you had all the items covered that you thought were necessary. And I'll talk about that a bit more later on. But let's first look at how availability is calculated, because as I've stated, availability can be measured on different factors. But a very important factor is the amount of uptime that a system has. And if you look at the availability as a calculated percentage of the amount of time that a system is up and down, available versus unavailable, then you come to a measurement that many of you probably have heard of, which is the measurement in the amount of nines. And the amount of nines is a description of the percentage of availability of the application. And to many people, this is a measuring stick that isn't as clear as it probably should be, or at least the implications aren't as clear as they should be. Because if we look at this table, what you see from this is that if you have just 4 nines, which for some is considered not that good, right? It still already results in only allowing for less than an hour of downtime per year, less than 5 minutes per month, 1 minute per week, or a downtime per day of a mere 9 seconds. And those are pretty stringent requirements. If you go to 4 nines and a 5, half an hour of downtime, less than half an hour of downtime per year, 2 minutes per month, half a minute each week, and just less than 5 seconds each day. So even small interruptions in service can already threaten these measurements, right? These levels of service that you might want to achieve. And of course, from there, it only gets worse. With 5 nines, you have less than a second of allowed downtime per year. And that hooks in back to the discussion about availability being planned or unplanned, because then the next complication arises, and that is that some measure these values without the planned downtime, where others would assess them including the planned downtime. Further complicating it is if your system only needs to be available during certain hours of the day or the week or the month or even the year, then availability during those periods could perhaps even be higher, or the requirement for that availability might even be higher than this, but the overall requirement may be very acceptable and lower even than these nines. And you must make the decision how you want to measure and what is acceptable to your business. So don't read too much into these measurements, but make sure that you understand their implications for your business and your infrastructure. Because as you might imagine, increasing levels of availability introduce increasing levels of complexity, and in turn, those deliver increasing levels of cost for the total solution. I'm keeping an eye on the question and answer section. If you have any questions, don't hesitate to ask them. I'll answer them at the end of the webinar unless they materially affect the flow of this conversation. It's time to look at the next part of this whole equation, which is the different ways of measuring availability. And we have several acronyms here, and they are sometimes in some areas well known, especially if you have system reliability engineers. For them, these words, these abbreviations are a standard part of their vocabulary, but to many people they're not. So let's dive into them a bit more. We're going to talk about recovery point objective, RPO. We're going to talk about recovery time objective, RTO. We're going to look at the main time to recovery, and we're going to talk about geographical redundancy. Recovery point objective. A recovery point objective is a not well understood aspect of availability, and I want to dive into it a bit deeper. If you look at your service and its continued operations, then availability of the service is of course important, but the transactions that are performed with the service can also be important, especially if you talk about a stateful application like Postgres, or basically any database that you keep long-term data in. When you look at that data, then the system is supposed to keep that data secure for you. So when something happens, you want to know how much of the data that was in the system was impacted. For instance, if you take a very non-digital approach to this, let's consider the idea that work is being done in an office using paper forms. And these paper forms are being processed and filed. Now, once they're filed, they are sent off to an archive, and all the business that was in these forms or described by these forms is processed. However, new forms come in, people do not have the time to process them all at once, and now suddenly a fire breaks out, and some of the forms are damaged or destroyed. Now, the thing is that everything that was on those forms is unique data. So once those forms are lost and they haven't been processed and the data being incorporated somewhere else, that data is lost. And the recovery point objective basically describes how much data may be lost in a case of an outage or a disturbance of the service. So what we're looking at here is, if something breaks, how much data do you actually lose in the process? And more importantly, can you reconstruct it from somewhere else to make the previous example digital again? If people get orders on paper forms and enter them into a digital system during the day, and at night the system then transfers those records to a remote system, then if something happens on the branch office where these forms are being processed and the system, the technical system, is lost, then the transactions that have been processed during the day are also lost, but they can be reconstructed from the paper forms. Much the same is going on if you look at a database system. So the recovery point objective basically states, across the level that you've defined, so either the technical system or the business process, how much data may be lost. If the technical system can hold a certain amount of back information, and you can reconstruct everything that would be lost if the technical system goes down from paper, you may have an RPO of 0. However, it may take you time to get back into full operation, which is the next topic of the topic of the next slide, and I'll get back into that. But we have to separate these two items. In other words, how much data may be lost in case of a problem, right? And how long does it take to get back to working service? And these two can be independent. They are usually interdependent, but it can be quite independent as well. So looking at RPO, the interesting information that you need to look at is, if records are lost, how much loss is acceptable to me? Can I restore from other factors? And this is usually described as either an amount of time or an amount of time that data is lost, or a volume of data that is lost. For instance, we may not lose more than a certain amount of forms, right? So looking at this factor, the next part that you need to consider is that if you look at survivability of a process, then there are two different scenarios basically. And we're not considering both scenarios in this webinar. Because one scenario is a disaster recovery scenario, where instead of a system, part of the infrastructure is lost, a larger part of infrastructure is lost, and you need to recover basically on a separate system or a separate location even to get back into operations. The recovery point objective for these two types of events may be different. For a disaster recovery operation, you might allow for a higher RPO than for an HA, a high availability systems outage, where you would ideally would not like to lose any data, if at all possible. So let's skip to the next part before we come back to this. And talk a bit about the time that you need to recover and get back into service. Because as I said, sometimes data is available in a different format and can be reconstructed digitally as well. But how much time does it take for your staff to re-enter the data that was on those forms? And are you able to keep continuing doing business during that time? So that means that if you want to be able to decide how much time you may lose before you start working again, you have to consider the recovery time objective. How much time are you allowing to go by after an incident before you can start working again? Famous examples of industries where this is a very critical factor are things like banks, organizations like banks, and other very transactional organizations where the business doesn't wait. And the recovery time needs to be very short, or the business will fail. So again, this is an extremely important objective for certain use cases. And it can even overrule sometimes the RPO objective in terms of that you rather return to service very quickly, even if it means a bit more data is lost that has already been processed, than vice versa. Is there any question around this topic at this point? Because this is a complex part of the whole equation, and I want to make sure that everyone is on board with this before I move on. Right.
We don't have questions, Gabby.
No, thank you. So if we look at RPO versus RTO, then the way that a business is supposed to approach this is by making a risk assessment and making sure that you understand what the cost to the business is for each of the scenarios that you go through. So this is also a risk analysis part, specifically for your data in this case, right? We'll talk about measures to get to certain levels of RPO and RTO later on. I'll move on to another measurement factor, which is called mean time to recovery. And the mean time to recovery is the mean time that it takes to have a fully functioning system again. And this is often used for certain hardware components. It's very well known for hard disks or physical systems, where if something fails, the amount of time that is needed, for instance, to rebuild a RAID array, which is a measure to improve the availability technically, how long it takes for it to fully recover to a nominal state. And again, this is for some organizations a very important factor. Other organizations see this as a measurement only applicable to parts of the system, whereas MTTR is never measured across the whole business process. So please be aware again that if you use this measurement, that it has certain aspects that are very applicable to databases, but it has also aspects that are more applicable to things like the underlying physical infrastructure. Which brings us to the last factor, which is the geographic or geography recovery objective. And that is more applicable to disaster recovery. In other words, if a large part of your infrastructure is gone or afflicted, how fast can you start up the operation with a minimal data loss on a different location? So this is basically an overarching recovery objective that is more applicable to large scale issues in your infrastructure. And again, as with the RPO and the RTO, you may measure these differently or have different demands of these for different types of modes of failure. So before you can make any assessment here, make sure that you really dive into what you want to achieve in terms of objectives with your business. And from there, decide which objectives apply and how you measure them. So it was a pretty long running leading to the part where Postgres comes in. And Postgres is a relational database, as most of you will probably know. And it is as a relational database, often the store for the most important data of your company, right? If you have data that is unimportant, then you could have it in files or have it somewhere else, but it's less important to you than the data that is in your databases. And that's basically the reason that relational databases are, and other types of databases, are so important for business, and why their availability is crucial for allowing other parts of the infrastructure to function. So the high availability for your database is exceptionally important. And we're going to talk about how to achieve that here. As we look at the earlier statement about what makes the availability of system and what influences it, then the general tenet of operational IT has been for the past decades, eliminate any single point of failure. And people go to great lengths to achieve that, making sure that there are duplicates of all essential systems, making sure that no single part of the whole system will negatively influence the availability. So in Postgres databases, to eliminate the single point of failure, what we basically advise is to make sure that you have multiple copies of your data. Postgres has an architecture that is centered around sharing no data between instances, in the sense that each of them has their own copy of the data to function with. But that also means that if you have data on a primary system, that you must have that data on a secondary system to be able to guarantee its survival in case of an issue. So if you look at eliminating a single point of failure, what we're doing here is making sure that data that is entrusted to the database is certain to be available on the secondary system in case of failure. And to that end, the data must be transferred from the primary system to the secondary system. And Postgres has had mechanisms for this idea since a long time already. And the original mechanism for this was wall shipping. It was the oldest way of making sure that your data was in two locations. The replication is based on the way that Postgres stores data on disk. And it does that by writing a serialized information of all changes to a so-called write-ahead log. In Oracle, it is called a redo log. In other databases, another system that has a different name. But what it is a description of everything that has gone into the database in terms of changes. Since these data points are stored in a file, if you ship that file, copy that file periodically to a secondary system and apply the changes there, you've achieved elimination of the single point of failure. However, with files, it'll always be chunk based. In other words, if just before one of these WAL files is copied, the system fails, the information that was stored in that WAL file will not reach the other side and will be lost, impacting your RPO. To mitigate this effect, later versions of Postgres incorporated something called streaming replication, which streams WAL files to one or more standbys, but immediately. Instead of waiting for a WAL file to fill and then copying it over, the systems communicate directly and information is transferred as soon as it is available and before or after committing the transaction to the client application. And the difference between those modes becomes obvious in the next few slides. Finally, there is also a logical replication, which is the last entry in Postgres to be added. And it allows you to selectively replicate data from a system to another system and to replicate between systems that are disparate in nature, either because they have a different operating system, for instance, or other parts of the infrastructure are different, so that you cannot use direct streaming replication or WAL file shipping. I've spoken about primary and secondary systems or replicas. And another way of looking at these replicas is that there are basically a copy of the primary system. They must be identical as much as possible for you to be certain that they operate in the similar manner. Obviously, if there's a failure of the primary that would cascade to the secondary, that would be an issue. So there's a few safeguards in place for that, and I'll get to those. It's good to remember that the way that Postgres is able to replicate is very, very flexible and diverse. A replica can be set up as just an HA replica, just as a high availability replica, or it can allow reading where certain queries are not put to the primary server, but are put to a secondary server. So besides a high availability measure, this can also be used, this mechanism can also be used to do read balancing, load balancing across nodes. However, for an HA replica, the main purpose will be to very quickly replace a failing primary or to switch over to, in case of planned downtime, where you do want to do maintenance, for instance. As stated, the major approaches are WAL shipping. Besides WAL shipping, the WAL files must also be archived for you to be able to do certain DR functionality, such as point-in-time recovery. These are not part of this discussion right now. To have a deeper insight into those, please look at one of our other webinars that are specific to this topic. Going on the topic of eliminating a single point of failure, what you see in this picture here is that the sender of this system is using WAL shipping instead of replication. So the WAL files are transferred through an archive command and then from there picked up by the replicas that can then incorporate the changes. You do not have to have just one replica, you can have a multitude of replicas, either all for HA or for different purposes. And the flexibility of Postgres means that you can even set up hierarchical replica series where systems basically percolate the information down to lower tiers. The specifics for Postgres are that the WAL files are normally about 16 megabytes in size. So for an RPO point of view, if you use this mechanism, then the maximum amount of data that could be lost here is that 16 megabytes approximately. There's a few details, but they are mostly around edge cases in terms of shipping and losing files in transit. But normally, that is your RPO is 60 megabytes. Now, the WAL files can be adjusted to different sizes, so make sure that you understand this aspect deeper if you want to use this mechanism. But we are here to help if you need more information on that. Just ask us and we'll get back to you on that. The system as it works is Postgres has a default way of saying if you want to archive the write-ahead logs, then please provide this command, tell me where to put them. And if that command completes successfully, then the database server is informed that it may reuse the file and continue on. Whereas the replicas will then pick up this file, apply it, and be able to serve the same data. The way that you monitor this WAL shipping is by looking at certain functions that return information to you within Postgres. Just a heads up, functions that are core functions in Postgres are always named PG underscore. So the first part of this name is always the same. And the labels that you see in these functions are quite descriptive. So for instance, PG is in recovery. If you execute that function, it doesn't take any arguments. But if you do that, then it will return either true or false, telling you whether the system is running recovery, which means that it is applying state information from another server. If you look at PG last xlog, and WAL replayed location or LSN, depending on the version that you're using. What it describes is where the standby is in processing this data. The last exact replay timestamp gives you an exact, literally an exact replay timestamp. In other words, it shows you where the transaction was replayed, the last transaction time replayed during recovery. If we look at these factors, then it does require a deeper understanding of Postgres. So if you want to know more about this, then you have to dive deeper into how these files are applied to the system and how they are generated, because they are dependent on the way that Postgres functions when it replicates data to a secondary system, depending on whether it's a synchronous replica, it's a wall shipping replica, it's an asynchronous replica, or a logical replica. So there's quite a bit going on here. And let's look at that aspect in more depth. If we leave the wall shipping example here, the architecture, and go to streaming replication. Streaming replication was available since the 9 series of Postgres. And what it does is skip the copying of the file, as described earlier. So the primary system provides the information for any secondary system that accepts it. So it basically retrieves the information. And Postgres has gained many features around this streaming replication in the past versions, so that you now have multiple ways of streaming the information and for the system to behave when that information is going to the other side. In asynchronous streaming replication, the information is made available to the secondary systems, and then the application that executed the transaction, so the end user application, gets a confirmation that the data was stored safely in the database. For instance, you are applying a delete of certain records, and you type in commit, or your application sends a commit, then the database will not confirm that the commit was successful until the data has been made available to the secondary systems. It doesn't guarantee, though, that the secondary system has the information and processed it. This is the asynchronous part of this type of replication, right? So it's asynchronous streaming replication. The amount of bytes that might be lost in an outage are lower than what you would get when you would use wall shipping, because, for instance, a wall file might not be full and get lost, whereas now every single transaction is individually transported and made available to a secondary system, but it may not have been applied because we do not wait for the secondary system to acknowledge that it has received the information. We simply say we made it available, it's up to the secondary system. Your RPO here is not 0. It's not guaranteed to be 0. It might be 0, but it's not guaranteed to be 0. So taking that into account, the next best thing that you could do is state, I want all data to be replicated to the other side, and I want to wait for confirmation that the data has arrived there before I'm going to tell the application, it's okay, you may continue, your data is safe. This is called synchronous replication in Postgres, and it has multiple levels, gained multiple levels of assurance over the years. What I mean with that is that if you use synchronous replication, what happens is that the primary system not just makes the information available to the secondary, but waits for confirmation, which means that there will be a time lag. And that is the reason that you have to decide if you want to do this, because the time it takes for the secondary system to confirm a transaction is delayed. That is the reason that you may want to select asynchronous replication after all, right? Otherwise, why wouldn't you select synchronous replication? Now, because synchronous replication and asynchronous replication each have their own benefits and drawbacks, what we've tried to do with Postgres is make sure that you have the flexibility to set it up in a way that fits you and your needs. For synchronous replication, that means that we created increasing levels of security of your data by stating that if you want synchronous replication just to confirm that the data has arrived at the secondary system, you can say that. If you want to make sure that the system on the other side has the data on disk as well, you can do that. The last step is that the secondary system not just confirms that it has received the data and it's on disk, but that it's visible to anyone querying it, like it was on the primary system. It's the highest level of consistency that you can get across these two systems. Of course, for every step that you take, the amount of delay increases because the secondary system has more processing to do and it takes more time for the confirmation to reach back to the primary system and then to be provided to the end user application. So what we've done is allowed you to create a way of having these systems, having multiple replicas and stating, I want to make sure that at least one of them has received the information and then you may continue. So the primary system can be told that it may continue, not just if one system acknowledges, but you can even say, if you're a higher level of security, that I want any certain amount of servers of a multitude of replicas to confirm that they've received the data, but not more. So after 3 of those in the middle line in this example have confirmed that they have the data, we can move on. Lastly, you can also influence these decisions with a parameter called synchronous commit, and the combination of these synchronous standby names and the synchronous commit configuration factor decide ultimately which of these is used in which way. If synchronous commit is off, obviously no commit is done to a secondary system. If synchronous commit is only local, then again, no remote system is consulted. Remote write means that it's arrived on the other side. On means that it is available when all the names or all the names of any 3, for instance, or first in the synchronous standby names have confirmed it. So the name here is actually a bit misleading. So on means that what is in synchronous standby names is taken into consideration, otherwise it will not be, right? And lastly, remote apply means that the secondary system has the information available for reading by its clients as well. So that's the highest level. We have a question around this. What process is responsible for log shipping into standby hosts? Is there any internal PostgreSQL process or daemon, or should I do it manually? Postgres is set up very, it's a great question, Alexander. Thank you for asking that. I'm going back to a slide before. So the wall shipping is done by a process that runs continuously, but it calls another process. So it's a hook that you have to provide your own solution for to ship these files. And that makes it very flexible, but it also makes it one of the more, how do you say that? It takes more work to set it up than for some other platforms. And that's by design, actually, because it also allows you to have the flexibility to provide your own solution precisely tailored to what you need. Usually a script is used, for instance, using rsync or SCP. And the trick here is that once that process returns true, in other words, it completes successfully, the file is considered transferred and is allowed to be reprocessed by the server. So in answer, yes, it isn't manually, right? The database server can trigger this process automatically, will trigger this process automatically, but you have to provide the way that it copies the files to a location that you have designed for that. Similarly, on the recovery nodes, you have to provide the commands in a script to get the files from that location. And again, once that file is copied over, then it's considered a working solution. So if it returns true, the script or command, then the file is considered copied and it will be applied. So how can you monitor streaming replication? We've already seen the parameters for WAL file replication, and they're partially applicable here as well. But for streaming replication, specifically, you have the PG stat replication and the PG WAL receiver views. These are not functions, these are views, and what they provide you is an overview of what is going on in your database. The primary here is the primary system, so there it's PG stat replication showing what is going on. On the standby, you will want to see what PG WAL receiver has received from the other side and how far it's processing that information. One of the aspects that impacts any system for high availability is how quickly and reliably can you detect issues and make a decision based on those issues on what to do next, and then to execute the process that you have designed to execute when something goes wrong in a certain situation. So if you look at this, then high availability in this sense is one of the most problematic parts of ICT. And the reason is exactly this. Before you want to take action, you want to make sure that you are taking action on the right information. And as we all know, sometimes automated systems have difficulty in making a decision because they don't have enough information, for instance. So it is critical that you understand that a large part of the time that you lose in switching over or failing over, it goes into detection and not necessarily into the switchover itself. And that is especially important with databases where if you do a switchover or do a failover, to put the precise name on it, then you may not be able to quickly fail back again. And to that end, you must make certain that you don't spuriously switch over just because a network connection was a bit glitchy or had a bit too much load. And the detection mechanism then decided, okay, the system is down. Let's start the process of failing over, only for the primary system to recover and come back up again. One of the other issues that plays in this is that you may then have a situation called collision, where you have two masters and both claiming that they are the primary systems, right? Two captains on one ship, and you get into an issue where your data gets corrupted because you have multiple nodes stating, I have the real view of the world. So after you've made certain that a system is in failure, the next thing you must make certain is that once you mark it as failed, it will not come back up and rummage all around your data in a way that wasn't designed. So mechanisms that do this and tools must provide these systems. In an HA system, the one doing the determination must, of course, also be redundant. Otherwise, the whole system is still having a single point of failure. And that comes back to the who is watching the watchers comment, sometimes made in different circumstances. But here it is very applicable as well. Your HA environment and everything that goes into it must not have a single node of failure, a single point of failure. So you must make sure that the solution that you choose for providing this failover mechanism is in itself robust. Once those items are guaranteed, then you can be sure that the application should not see an issue when there's a systems issue. Right? So the client application shouldn't notice when your system is having an issue, or if you're doing maintenance or any other way of influencing its availability. To that end, EDB has several tools. For Postgres, we use our Failover Manager, and what it does is exactly this. It is agent-based, and the agents work from each database to monitor it and its operating system. And they, through a chatter mechanism, discuss the health of the system. Once they detect a failure, they can switch the database from the primary to a secondary, a replica, reconfigure the virtual IP address, or use a load balancer software in front of it, or your load balancing firewalls, all integrated into this tool through hooks that you can use to reconfigure your infrastructure. When you have two captains on the system, that leads to issues. So to make sure that that doesn't happen, what EFM also does is it avoids this split brain scenario where it basically shoots the other node in the head. Right? It's the default go-to way of achieving this, and we've used it as well. So what it will do is it prevents a failed primary from standing back up like a zombie and mingling in the crowd again. So it can't rejoin a cluster of nodes where it has failed. Another aspect of EFM that makes it very interesting is that it automatically fails over to the most current standby. In other words, if there's multiple replicas, it will not only determine that there has been a failure, but it will then also determine which of those replicas has the most up-to-date copy of the data, if there's any difference between them, and then decides on other factors which one to promote. So bringing that all together in one picture, what you see at the top is the client application. It is the view of availability. It has the full view of availability across the stack. Underneath, what you see is a load balancer. It could be a virtual IP with using an application that can recover from any issues itself. It can be another mechanism that you use. And these are a front end to the underlying databases. And you see on the left, the primary. You see in the middle one or more standbys that get the information from the primary. And on the right, what you see is a witness node, which is sometimes needed to achieve quorum and to make certain that if there's an outage, that you correctly decide which of the hosts has an issue. Right? If you have two DCs, one fails, you must make certain from the outside which DC has failed, because if both of them can't reach each other, they might both get the impression that they are winning the last standing party. So a witness node helps solve that issue by providing quorum. So how does this come back to RPO, RTO, MTTR, and GPO? Let's talk about that. The aspects that we've discussed are about HA, but HA is more than just the systems being available all the time. It's also about coming back if there's an issue where you quickly need to recover some data. So this is not a complete DR situation, but you've lost some more information and you want to make the RPO as small as possible. Then there's still one other tool that you can use in our arsenal, and that is the backup and recovery tool, because what it does is it not just makes a backup and restores it, but it also keeps the WAL files safe, and those can be used to recover quickly. In a DR situation, what happens is that you still need to get back into operation quickly. So the speed of your recovery from data that comes back from your backup or your other storage system basically impacts your RPO and your RTO, because RPO here can be very good, right? You may have the last bits of data, but if you have to restore everything onto a new server because for whatever reason, the secondary wasn't there or it wasn't set up correctly, you have to do a recovery. And in this case, what you get is that you must take into account how much time it will take then to get back up and running. Why am I saying this? Even though this isn't about DR, It's up to you to make a decision, a business decision, on how much effort and cost you are willing to invest to make the RPO and RTO very low under all circumstances. If the time that it takes, even with our backup and recovery tool and all the best intentions of your people, to get back up in a few hours, but you have a RTO requirement that is a few minutes, then that will never be used, right? If your company fails, if the system is down for a few minutes, then it doesn't matter that there's a great backup and you can get back from it. It simply doesn't matter anymore, right? The backups are installed, or as we would like to say it, operations is a complete success, but the patient died. Not a good look anywhere. So looking at this aspect, it's one of the considerations that you have to make in your time. And unfortunately, I missed another question. So if you do not mind, I will answer that question on EFM at the end of this session. So what does BART do? It provides you with a central repository and catalog for all backup data. It can do restores, and in that sense, it is handy for DR. It is handy to recover from logical problems like an operator making a mistake or data being damaged by a misbehaving system. And I'm not going to go too far into this, but when it comes down to what our BART tool does, it creates a full backup, it can create block level incremental backups, and it does wall archiving. And these 3 levels allow you to reduce the amount of time that you need to recover from backup. So when you make these calculations and assessments of what risk you're willing to take or what you're able to take, please have a look at our backup and recovery tool before you decide that you need to go for a very, very highly available system, whereas the cost for that would be usually quite high, whereas a backup solution that would allow you to achieve your goals in just as well might be fine for many situations. So I'm not trying to tell you not to do an HA solution, but you do have to realize that it brings complexity and cost with it that are usually far higher than a good backup and recovery solution that might give you fine and acceptable results anyway. Going to the high availability back again, the monitoring of your solution is essential. Why? Because replication is the backbone. If it fails, at that point you become vulnerable. So you must always know the status of the replication, of the application of the replicated data on the secondary systems, and you just want to have a good overview of what's going on in your system. To that end, what we've done is create PEM. PEM is our Postgres Enterprise Manager. The name is not very imaginative, but it clearly depicts what it does. And it allows you to have a great look across your database landscape, your Postgres and EDB advanced server landscape, and determine its health, look into any issues that you have. You can do drill down on things like wait states and other aspects, but it also allows you to monitor replication. So it shows status information like performance. Is your secondary system not just up to date, but is it barely keeping up with the stream of data it's receiving, or is it easily flowing along, applying all the changes, perhaps even answering questions, right? So this tool is a tool that it goes further than just monitoring, but for high availability. The big benefits are in being able to see these thresholds, have graphs around them, and provide alerting to, for instance, your alerting system, a Nagios or an SNMP-based Zabbix, for instance, system that will ping your administrators if anything is wrong. To that end, what it does is it has its own infrastructure. It can monitor these systems through the agents installed, or it can do it agentless. But in the end, what it does, it stores the information so that you don't just have a very current view of your infrastructure, but you can also look back over history of what was going on and provide you insight. For instance, when is a system suddenly slowing down? Does it have to do with replication? Is replication suffering because of a batch workload or a large increase in the amount of transactions that's going on? Well, you need this insight. And whatever tool you use, make sure that you watch those replication factors that we discussed earlier, on the earlier slides. We're going to the last few slides here, talking about maintenance and planned windows, but I'm also coming up on the hour. This presentation took a bit more time than I thought and practiced. So apologies for that. I hope you can stay around for the questions as well. So maintenance window and planned downtime. If you look at the reasons why people have planned downtime, then it basically comes down on the hardware side, replacing or fixing systems, or on the software side. And there too, it's about replacing or fixing software. So the main reasons are to remedy issues that you've come across, either because software has a bug or because something needs to be changed that cannot be done while online. Sometimes to increase the whole infrastructure and architecture so that it becomes more reliable. And finally, of course, the most annoying and dangerous ones, security issues, where not patching can mean loss of data, damaging of data, or other aspects that may influence your business in both technically in operations, but also in your perceived value in the market. So to update software, there are three strategies. You can do all nodes patching, you can do rolling patching, and you can do minimum downtime patching. And since we're talking about HA, the all node patching strategy is usually applicable if you have a service window where downtime doesn't matter. Then it's a very fast and reliable way of making sure that everything works, that you have a rollback opportunity, and that you can fix any issue if it arises during the upgrade or after the upgrade without going through a lot of hassle. The second one is rolling patching, which is more convoluted, where you first patch standby servers and then switch over to one of the now upgraded servers. And this is a controlled switchover. It's done by EFM, where the previous primary will be reconfigured as a secondary after the upgrade, after which you can, of course, switch back again using EFM. Lastly, we have minimum downtime patching. And now I've mixed up the scenarios. I apologize. Sorry, minimum downtime patching is the scenario I provided first. A rolling patching is where you patch them one after a time, but where the master is patched, the primary is patched separately and then brought back up. It takes a bit more time and may disallow writes, but if you have reads available on the secondaries, that may not impact your business much or at all. So this is a scenario. Rolling patching is where you can, for instance, pause the front-end application from providing write or delete changes to the database, so that you have this window to update the primary very quickly, but still with some downtime for writes. The last scenario is minimum downtime patching that I described earlier as being done with a switchover where one of the replicas take the place of the primary. Conclusion. We've made it. Looking at your landscape, what you need to do is make sure that you look at the design considerations. What do you need in terms of the measurement sticks that you were given? Under what circumstances? What risks to your business and to the operation of this application are there? And how big is the chance that they arise. All of these will influence your decision how much time, money, and effort you're going to put into each of these different architectures. Whatever your choice will be in the end, the conclusion must be that Postgres has all the technology, all the features to provide you with very highly available infrastructure, as is shown by the customers that we have and are using this system with all these tools, right? So we have the streaming replication, we have the failover manager, we have the enterprise manager, and the backup and recovery tool. And these components allow you to make a highly available architecture where the measuring sticks that you define for the periods that you define are the only thing that limits you in your choices. If you need more resources, please have a look at some of our blog series or follow some of our other webinars. There are webinar recordings on our website as well, so do not hesitate to browse through our catalog and see if there's anything of interest to you. Finally, I want to do what some others do up front. I want to tell you a little bit about EDB. If you already know about us, don't worry. We will get into the questions and answers directly afterwards, so please stick around. But the reason that we feel that we have the authority to provide you with these solutions is based on the fact that we've been doing this for a long time now. Postgres has existed since the early days of relational databases in different forms and through different parents, basically. But it has become the de facto open source relational database, and one of the few databases that is capable of handling almost any type of workload that a database can handle, including things like NoSQL workloads, key value store, geographical workloads. And with those, we have cemented our existence in the Gartner Magic Quadrant for a lot of years now. And we're here to stay. Postgres is here to grow. Postgres is on the same trajectory as Linux was not that long ago, and you know where it ended up. We foresee that Postgres will be the next open source piece of software that's going to make a big impact in enterprise. And we're already making a big impact as EDB with Postgres or advanced server, with many of these customers deploying our database as a core mission critical system, not as just a side database. EDB does this by having a lot of the knowledge around Postgres in-house, right? Where Postgres is an open source project, EDB has taken an important role in this community, whereas we fully respect and work with the community when it comes to Postgres. What EDB tries to do is add on top the enterprise features that you may need for high availability, backup and recovery, or other aspects of your operation. The next webinar is on November 25th. It's an overview of reference architectures for Postgres by Michael Willer. And we'll provide the slides with all this information and all the links after the call. I will get to the questions now before ending. And the question here was from an anonymous attendee. Does EFM work with Postgres Community Edition? And what difference between EFM and the open source solution like Patroni are there? And witness nodes, could they be standbys in Postgres? So those three questions, and I'll answer them in turn. Yes, EFM, like all our tools, works both with our advanced server and with the community Postgres. However, if you want to use them, they're not open source, so you would have to have a subscription with us. And that's a commercial discussion, but the subscription prices are dependent on if you're using the community version or our advanced server platform. But the tools work with both. And you can deploy them on basically any type of underlying architecture, like containers or VMs or physical machines or in the cloud. That doesn't really matter, as long as the architecture that you use is able to work with EFM. And that's more of a question of what kind of system do you use, and is it reachable for EFM? If you want more information on that, then there are specific webinars on the use of EFM and blogs on that topic. What are the differences between EFM and the open source solutions like Patroni? It's a very good question. Each of those solutions has their own benefits and drawbacks. When it comes to Patroni, it is basically made for one type of platform, which is a container or Kubernetes-like platform, whereas EFM works across the board. A witness node is normally in EFM a host that doesn't run the database software. It's just the agent. But of course, you could install that agent anywhere as long as it's able to connect to all the machines that it needs to keep contact with to determine their health. In other words, if you use a standby, then make sure that all the hosts in the cluster are reachable from that standby, and that the standby has enough oomph to do both its functions. But it's more about quorum, right? You need a witness node if you have to have a tiebreaker. If you don't need a tiebreaker to decide which part of the infrastructure is still functioning healthily and which part isn't, then this is less of an issue, and you can use one of the witness nodes as or one of the standbys as a witness node. Thank you for being so patient and staying with me. Are there any other questions that I can answer?
I don't think we have any more questions. So, well, this takes us to the end of today's session. Thank you very much, Gabby, for this insightful session, and thank you for everyone for attending. We will be sharing this recording along with the slides with you as soon as possible. You will get this to your inbox, to the email address you used to register for this session. I have shared with everyone the link to register for our next webinar. We hope to see you there. Well, I hope everyone has a great rest of your day, and thank you very much for joining again.
Thank you, Monica. Thank you, attendees, and I hope to hear from you if you have any further questions or want to contact us. Have a great day. Goodbye.
Goodbye.
Oh, wait, just a second.
Sure.
Somebody's raised a hand. Is there a question or? Okay. I think that people are using that to say goodbye. Thank you and have a great day.
Bye-bye.
Bye-bye.